Hey guys, so we're given this problem. Plutonium has a half-life of 50 years. Obtain a formula for the amount of plutonium present after T years. How long will it be before 1/4 of the original amount has disintegrated? What fraction will disintegrate during the 1st, 3rd, and 10th century? So we were given the half-life of plutonium, which we will denote as T subscript 1/2, which is equal to 50 years. And the formula that we are going to use in this problem is A equals A naught times E raised to the power of KT. This formula is usually used for growth and decay problems, but it can also be used for finding the half-life of chemical elements, since this is a problem of disintegration or decay. Now, in this equation, we don't know the value of K yet, so we should look for that. And we will use the given half-life, which is equal to 50 years. So here I substituted T with 50, which is the half-life, and since it is a half-life, and by definition the half-life is the time required for 1/2 of the original substance to disintegrate. So since A here is the amount remaining and A naught is the initial amount of the substance, we have during the half-life 1/2 of the original amount remains. So by using this equation, you can see that A naught here cancels, which gives us 1/2 equals E raised to the 50k. Since we're looking for K, we need to bring it down. And to do that, we have to apply natural logarithm to both sides in order to cancel E. So doing that, I just converted 1/2 here into 0.5, since they're still equal. So we have ln of 0.5 equals ln of E raised to the power of 50k. And then we have, since ln and E cancel each other, we have ln of 0.5 equals 50k. And then dividing both sides by 50, we get the constant k to be equal to ln of 0.5 over 50. So let's solve the first problem, the first question. Let's answer that. So what I did here is I just substituted the value of K, which is ln of 0.5 over 50, to the original equation. So we have here A is equal to A naught times E raised to the power of ln of 0.5 over 50 times T. And so this is our solution, our equation in finding the amount of plutonium at any time T. And then let's go to the next question, which is, how long will it be before 1/4 of the original amount has disintegrated? So again, we use our equation, which is A of T is equal to A naught times E raised to the power of ln 0.5 over 50 times T. So since the question is how long will it be before 1/4 of the original amount has disintegrated, so when we say 1/4 of the original amount has disintegrated, it means that 3/4 of the original amount remains. So remember that A here represents the amount remaining, not the amount that has disintegrated. So when 1/4 of the original amount has disintegrated, it means that 3/4 of the original amount remains. That's why we have here 3/4 of A naught is equal to A naught times E raised to the power of ln of our K times T. So again, we are able to cancel the A naught, and I just converted 3/4 into its decimal form, which is 0.75. So we have this equation. And then I applied the natural logarithm to both sides in order to cancel out the e right here. And then we are left with the equation ln of 0.75 is equal to ln of 0.5 over 50 times t. Dividing both sides by ln of 0.5 over 50, we get t to be equal to ln of 0.75 times 50 over ln of 0.5. And when you compute that using your calculators, we're going to get t, which is equal to 20.75 years. This means that after 20.75 years, 1/4 of the original amount has already disintegrated. Okay, that seems reasonable because we have a half-life of 50 years. So if you get an amount of t that is beyond 50, I'm sure that your calculations are wrong. Okay, let's move on to the next question. What fraction will disintegrate during the 1st, 3rd, and 10th century? Okay, so again, I have written our equation right here. Then this is just to remind you that A is the amount remaining. So A over A naught is the fraction of the amount remaining. So we have to be careful here. This is not the fraction of the amount that has disintegrated. This is the fraction of the amount remaining. Okay, just want to be clear on that. So this is pretty obvious. The 1st century is, of course, a century is 100 years. 3rd century after 300 years. You have 10th century after 1,000 years. Wow, that's a long time. Okay. So during the 1st century, again, we have our equation, and I substituted 100 here since, again, this is a century, 100 years. And then computing that using the calculator, we have A over A naught is equal to 0.25. Again, this is the fraction of the amount remaining, not the fraction of the amount that has already disintegrated. So in order to find the amount that has disintegrated, we need to subtract 0.25 from 1. So we are left with 0.75. So this means that after a century, 3/4 of the original amount of the substance disintegrates. Okay, so let's move on to the 3rd century. So this is the process here is pretty much the same. It's just that you substitute a different value for t here, so that should be simple enough. And then after calculating that, we got A over A naught is equal to 1 over 64. So that is the fraction of the amount remaining after the 3rd century. And so subtracting that from 1, we have 0.98 disintegrates, or 98% disintegrates. So it almost is gone, right? Okay, oops. Okay, so after the 10th century, again, all we did is to substitute 1000 for t here, and then we got 9.54 times 10 to the negative 7 as the fraction of the remaining plutonium. So subtracting that from 1, we get 0.999 disintegrates. So this means that after 1,000 years, only a negligible amount remains. So that's reasonable since 1,000 years is a long time. Okay, so I hope you get it. Thank you.